All right, let's come to our content here. So we are Chem. And it would also be really good if you could all turn on your cameras. I know some of you messaged me earlier that you couldn't, but it would be great if you can, because I know I'm teaching students rather than letters. Great, thank you, Pranav. Thanks. Okay, so you should all be able to see my screen now. Let's get started. So recap from last lesson, I'm just going to start asking you all a bunch of questions. Tanisha, Gibbs free energy change. If it's less than 0, comment on reaction spontaneity.
If delta G is less than 0, then the reaction is spontaneous.
Good.
And if
I'll
it
take Pranav now. Pranav, if the Gibbs free energy change is greater than 0, can you comment on spontaneity?
It's non-spontaneous.
And what if it's between -10 and +10?
In equilibrium.
Good. And going on to Ansh. Ansh, what are the two drivers for a chemical reaction?
Enthalpy and entropy.
Good. I want you to be more specific, remember? Those are categories, but I want you to tell me, is the drive to higher or lower enthalpy, and the same for entropy?
A drive to higher entropy and lower enthalpy.
Very good. Right. So we'll go to Athava now. Athava, combustion reactions, are they typically spontaneous or non-spontaneous? So your first syllabus dot point is investigating these reactions here. So the two I've circled here, do those tend to be spontaneous or non-spontaneous, and why?
They're spontaneous.
Good. And why do you say that?
Because it goes for a higher entropy, because like the particles are like getting more disordered, and
Good.
it's also lower enthalpy because it's delta H is negative.
Very good. Good job. Right. And we'll come back to Pranav. Pranav, what would the delta G values be for the first two reactions?
They would be non-spontaneous. No, like equilibrium, kind of.
So it'd be between -10 and +10. Very good. All right. And I guess final question, Tanisha, open versus closed system. What's the difference?
in an open system, the matter and energy can be exchanged with the surrounding environment, whereas in a closed system, only the energy can be exchanged with the surrounding environment.
Very good. I'm very impressed. You all nailed it, right? And finally, I'll throw this last question at Ansh. Ansh, I want you to define. Actually, Rabab, you haven't answered one yet. So, Rabab, the Chatelier's principle. Define it for me.
If a system is disturbed, then it will adjust itself to the direction to counteract the disturbance.
Okay, nice. Hi, Riyasat. Sorry, Riyasat, we're just going through what we learned last lesson. So the same as what you learned on Sunday. Okay, so I'll ask you a couple of questions too. So Riyasat, we're just talking about equilibrium. Rabab defined it as, so Rabab, anything else, or anyone in the class for that matter, is there anything you'd like to add to Rabab's definition? She's missing one very important term. She mentioned when a system is subject to a disturbance, it'll favor the reaction to counteract that disturbance. Is that right, Rabab?
Yeah.
Good. What else would we add on top of that? It's two things I'm looking
If the system is a dynamic equilibrium.
Very good. Good job. So a system in dynamic equilibrium is subjected to a disturbance. It'll favor the reaction pathway. And Pranav, do we just say counteract, or do we mention something in front of the word counteract?
Temporarily counteract.
Ooh, there's another word I'm looking for. Riyasat, is it a complete counteraction or a partial counteraction? It's Le Chatelier's principle.
It's a partial counteraction.
Very good. So you'd want to include that in your definition. So summing this all up, what all of you have told me is that Le Chatelier's principle states that when a dynamic equilibrium is subject to a disturbance, it'll favor the reaction pathway to partially counteract that disturbance and return to equilibrium. That would be a perfect explanation of LCP. Does that make sense to all of us? Good. Now, I gave you 3 questions that you can use and apply to any LCP question. What are those 3 questions, Anj?
What is being changed?
Good. Keep going.
What is the opposite of the change?
Good. Ed?
And what direction?
Good. And Riyasat, what are the 3 different ways that you can disrupt an equilibrium? So regarding question 1, what are the 3 ways we can disturb an equilibrium?
The 3 ways are changing the concentration.
Good.
And there's changing the pressure or volume. And the third is changing the temperature of the system.
Good job. So today's lesson, what I'm going to be introducing you all to is number 1, we're going to be answering harder the Shadowless Principle questions. Then we're going to go on to our graphs, which are very high yield. So this will be a very important lesson. Let's jump right into it. So how about we start by answering some questions? So with a reaction such as this, I want you to imagine that what we've done is we've doubled the volume of the vessel, doubled volume. I'm going to give you all about 10-15 seconds to think about the reaction pathway in which we favor, and I want you to work towards an exam articulated answer now. So last lesson I taught you all the 3 fundamental questions to conceptually think about OCP. Now your goal should be, how do I write it in an exam to get full marks? I'm going to be very picky with your wording here. So we've doubled volume of this system. You can do the rest of these questions for homework, but I want to go straight to pressure here. So we've doubled volume. I want you to quickly jot down your book. What would be the key things you'd mention? This is a very important reaction. This is called the Haber process, and we produce this ammonia to enrich fertilizers to meet our global food supply. It's a very, very common reaction. So if I was you, I'd probably memorize this reaction while I can. It's exothermic, and it's nitrogen plus hydrogen gives you ammonia. All right, I'm going to pick on the student that currently probably has the most exposure to this. So Pranav, you've done a couple of these questions. Take us through it. What would your answer be? We've doubled volume. Explain the effect of doubling volume on equilibrium. I want you all, everyone else, to focus on critiquing his answer. What is he missing? What did he do well? Okay, take it away.
Okay. Wait, should I just like break it down first and then put it into sentences, or like just say it?
Word for word, what's your exam answer? That's what we're looking at here.
Okay. Doubling volume in this system will decrease the pressure of the system. According to Le Chatelier's principle, this will partially, according to Le Chatelier's principle, there will be a partial change in the system where it will have an increase in pressure, favoring the left-hand side of the reverse reaction.
Okay, good. Now I'm going to ask the rest of you. So good job, Pranav. I'm going to ask the rest of you. What else would you change? What was missed? What did you do well? There's a lot to learn from this answer. So I will start with this now. Tanisha, there's 3 basic questions. What was the change? What was the opposite? And what was the direction? Fill that out for us. So what was the change?
The change was the concentration and volume, technically.
Okay, now one thing I want you to remember is concentration. We use that term when we're talking about one of the substances. Since all of the substances changed in concentration, because as you all know, C equals N on V, when you double volume, you've halved concentration of all the gases. Does everyone agree? Now, the reason which we won't mention concentration, Tanisha, is because in the HSC, concentration refers to one substance.
Okay.
So you need to say pressure or volume in your answer. So again, what was the stimulus?
So pressure and volume are both changed.
Okay, you need to be very specific here. Have they increased or decreased?
Okay. So pressure goes to half of its original amount, and then volume was doubled.
Good. That's what you need to mention word for word. Okay. Next, Pranav, what's the opposite of that?
You need to have a decrease in pressure, increase in pressure.
This is why if you say the stimulus is a change in pressure, you've stuffed yourself up, because what's the opposite of a change in pressure? Makes no sense. The opposite of a decrease in pressure is an increase in pressure. That's quite intuitive. Now, Riyasat, which direction would we go if we want to increase pressure?
The reverse reaction would be favored since there are more there are more moles of gases in the reactants than products, which increases the pressure of the system.
Now, what I would mention word for word in your exam answer is you must state the gas molecules on the left-hand side and on the right-hand side. They check for this, everyone. And if it's in the marking criteria, you lose easy marks by not mentioning the gas moles on the left and on the right-hand side. So I'll show you how I'd word it. But for now, whenever you're approaching these questions, block off the left, block off the right, and write the number of gas moles on the left and right. Make that your habit. So you always state the numbers. So Pranav, the first key point I want you to improve is in future, if I ever ask you a question like this, you must tell me gas moles. Otherwise, it's a mark lost. Okay? So in my exam answer, we'll come back to that soon. But finally, what's the direction? Athava? We're trying
I'm
to
not sure.
So Athava, we're trying to increase pressure. So we want to make more gas moles, right? Because if you make more gas moles, there's going to be more collisions against the gas moles,
Yeah.
the walls of the vessel.
Then the reverse reaction would be favored.
Exactly, right? So we're going to favor more gas moles because you want to increase pressure. So it's the reverse reaction. Now, I'm going to tell you my exam answer so you all can pay attention and look at the wording here, right? So so the question is doubling volume. So I'd mention when volume is doubled, the pressure of the system is halved. So I've identified the stimulus. That's 1 mark. Mark number 2. When pressure of the system is halved, the Shadowless Principle predicts that the reverse reaction will be favored to favor the production of 4 moles of gas versus right-hand side, bracket 2 moles of gas. As a result, the pressure will be partially increased and the system will return to equilibrium. Do you see the slight differences that I've made here? I followed the same basic 3 steps. Stimulus, opposite direction. But the thing with gas moles, and this is very important, whenever you ask a pressure volume question, you must have the number of moles on the left-hand side and right-hand side written in your answer. Does that make sense? So get a red pen and write that down because that's a super easy area where students make a silly mistake. And that's why I specifically picked volume as our stimulus for this question. Do we have any questions so far? Okay.
This is a question not relevant to this, but just asking if I should also notify Midlash, Maher, and all of them to join this.
Yes, that would be really good. I was waiting.
I don't think they saw it either.
Yeah. Perfect. Thank you, Riasat. Appreciate it. Yeah, I've recorded this entire lesson so they can catch up on the previous section of it. But yeah, it'd mean a lot if you could let them know. Thank you. All right. Let's go to question B. This is much easier, but I want you to focus on perfecting your answer. Okay? So I'm not going to pick removing nitrogen. Let's make the stimulus an increase in temperature. Right? So explain the effect of increasing temperature on this equilibrium. Again, focus on your articulation. I know you all know the 3 questions. I know you can answer the fundamentals, but I want you to work on getting 2 marks out of 2 marks. I want to see you all speaking out loud. The beauty of being muted is that you can explain things out loud, and that's when it will stick. If you just write things down, I promise you, you'll be much slower than your peers who explain and teach it to themselves. So what is going on? About 10 seconds, I'll ask one of you to tell me your answer. Okay, Athava, I'll get you to start off by explaining the conceptual side of things. So Athava, you can follow these 3 steps, especially when you want to answer questions formally, but do you know any shortcuts to very quickly identify the direction we go? Or any tips?
Seeing as it's maybe because like since it's an endothermic reaction and like there's an increase in temperature,
Pause for 1 moment.
Forward reaction.
Pause for a moment. Is it endothermic?
Oh no, sorry, exothermic. My bad.
Good. So tell me, does heat belong on the right-hand side or the left-hand side? If I were to write heat as a product or reactant, where would it sit?
On the right-hand side.
Very good, right? So a little tip I'll give you all, what I was looking for is if you see heat is negative, when you bring it into the reaction, you swap the sign, so it becomes positive heat. Does that make sense? So that tells you it's an exothermic reaction. Now you treat this like any other reactant, right? So what I do is instead of writing out, stimulus opposite direction, I do a little faster way, which is the same principle. I go, well, what was the stimulus? It was an increase in temperature. What's the opposite? We're trying to decrease temperature. How do I decrease temperature? I use temperature up. Does everyone agree? So we favor the reverse reaction. That's it. Right? So I've still gone through those 3 questions, but I'm not writing stuff down. I'm just drawing arrows. So that's how I want you to get to now with your HSC chemistry knowledge. Just using 3 arrows, you should always get to your answer regarding equilibrium. All right, so now let's work on the wording here. I want you to work on 2 things, being concise and not missing key points. You need to find balance. So let me ask Ansh, you're going to give this a go.
As temperature is increased in the system, the state of equilibrium has changed. The Shadowless Principle therefore needs a partial change to decrease the temperature. This is done by favoring the reverse reaction.
Okay, good. Look, I'd give you full marks, but I'd say your middle sentence wasn't necessarily needed, right? You can add the partial in your second sentence. What I mean by that is, maybe I'll get one other person to explain it before I do. Reset, what would your answer sound like?
The system has the system experiences a disturbance as the temperature is increased, and by the Chatelier principle, the system will attempt to decrease the temperature by, and since the reverse reaction is endothermic, so which means it absorbs the energy and heat, the reverse direction will be favored.
Okay, good. I can see your conceptual understanding is very good. You've understood that to a T. The one thing I want you to work on, Reset, is less sentences to explain the same meaning. Okay, so I'll show you what I mean by that. Sorry, do you mind just muting just because I'm getting echo of my voice? Perfect, thank you. So my answer would sound like this. So just compare it to yours, right? So I'd say, when temperature is increased, Le Chatelier's principle predicts that which reaction will be favored, everyone? Endo or exothermic? That's the first thing you want to identify. If temperature is increased, what did we say?
Endo.
Yeah, so my answer would be, when temperature is increased, the Chatelier's principle predicts that the endothermic reaction will be favored to partially counteract the change. Thus, the reverse reaction is favored to return to equilibrium. Do you see I've answered the question in 2 lines? And my 2 lines mention all the key points. I want to hear whether we'll be favoring the endo or exothermic reaction, right? And I'd also want to know what direction we're going. That's the key things. You need to mention the words endo or exothermic in your answer. That's the key principle that I'm getting to. Does that make sense? If you don't mention that, then you can lose marks for temperature. Okay, so have a look at your answer and have a look at whether you've mentioned the word endo or exothermic. Can you raise your hand if you have? So hit the raise hand icon if you use the word endo or exothermic in your answer. Good, good. That's very important. So what I'm trying to cue you into is perfecting your answer. You want to get to the point where LCP is 3 marks, okay? Because that's exactly what LCP is. It's not hard at all once you understand the key principles. Very good. And what we'll do is I'll throw you into a slightly challenging question. Oh, there are 2 good questions for you. 2 exam questions, 1 and 2. We'll start with 1. I'm going to give you all 10 seconds. So I'll give you 10 seconds to read it and 10 seconds to tell me which direction. Oh, is it endo or exothermic? You have 30 seconds or so to get to your answer. In your HSC, it's actually very unlikely you'll get a simple LCP question because they're too easy. So you might get questions where it's slightly different order. So raise your hand if you've got an answer. Don't worry about your articulation for now. Do you conceptually have an answer? Is this reaction endo or exothermic? That's what I want to know. And then those of you who've got an answer, start working on how you're going to articulate it. All right, so let me start asking us. So, Tanisha, forward reaction, is it endothermic or exothermic?
The forward reaction is an exothermic.
Okay. Ansh, agree, disagree? Forward reaction, what is it?
Oh, endothermic.
Got endothermic. And Riasat, what's your final answer?
Good. Endothermic.
Okay, good. Now, remember, what did I tell you? With any LCP question, no matter how varied it is, Pranav, what are the 3 things we do?
The 3 questions. So stimulus, opposite direction.
Yeah, I just remember SOD by now because I've written it so many times. Stimulus, opposite direction. So what was the stimulus, Pranav?
It's being increased. Yeah, increase in temperature.
Good, right. You almost gave me a vague answer. It's the worst thing you can do for stimulus. A vague answer will stuff your entire answer up. So an increase in temperature of the system is a stimulus, right? What's the opposite of that, everyone?
Decrease.
Good. And when we decrease temperature, Athava, are we favoring the endo or exothermic reaction?
Could you say that again, please?
If we're decreasing temperature, are we favoring the endo or exothermic reaction?
If you're decreasing it, we're favoring the endothermic.
Good. We're favoring the endothermic reaction. Very good. So which direction are we going here? It's turning blue, so what does that tell you? Right or left? If it turned
Right.
blue, does everyone agree this product here, your cobalt chloride, has increased in concentration? You've shifted to the right-hand side. So we've gone to the right-hand side. Put 2 and 2 together. We wanted to favor the endothermic reaction, and we've gone to the right-hand side. So the right-hand side must be endothermic. Does that make sense? So the answer is this reaction is an endothermic reaction. Tanisha, does that make sense? Can you apply those 3 questions? Very good.
I'm sorry, could you repeat why it's to the right hand?
Okay, sure. So which direction did we go based on the stem, Rabab? We can see when we heated the reaction, Le Chatelier's principle tried to counteract the change. And what direction did we go?
To the right.
Why did we go to the right? Can you see the solution is more blue in color? The stem has mentioned that.
Yeah.
Make it more blue in color. You have to increase your product or go to the right. So that's how I know it's gone to the right.
Okay, yeah, that makes sense. Thank you.
Good. Good. Very good. Good job. So now, how are you going to word this? That's your next question. Again, I'm going to give you about 10 seconds to, I want you all to practice saying it out loud. Okay? Because when I ask one of you, it better sound like an exam structure, at least your best effort. You have 2 lines. Any more than 2 lines, and it's too much words. Athava, I want you to give this question a go. What does your exam answer sound like?
There is an increase in temperature, which disrupts the system, and according to Le Chatelier's principle, it predicts the forward reaction will be favored. In order to partially counteract the change.
Okay, everyone, did you hear that answer? And did you hear the word endo or exothermic in that answer? So did you mention the word endo or exothermic, Athava?
I wrote it at the start, and I just didn't say it.
Good. Okay. So remember, the one thing I told you with temperatures, if you don't mention endothermic or exothermic, that's a mark lost. Okay. So I want you to get a red pen and write that. The goal of chemistry is to make all your mistakes with me in class, so you don't make a single one in that exam hall. Okay. So I'm going to show you all my explanation. I always start my answers with Le Chatelier's principle predicts. That's a really good way to start an LCP question. Okay, so for this question, I would say Le Chatelier's principle predicts that when the cobalt chloride solution is heated, the endothermic reaction will be favored to partially counteract the increase in temperature and return to equilibrium. As the solution increased in blue intensity, the forward reaction was favored, thus the forward reaction is endothermic. Do you all see how I've mentioned the word endo and exo? Do you see how I identified the stimulus? And referred to the Shadowless Principle. And I've even spoken about partially counteracting the change. So that's how your exam answer should sound. So key point is, right, if I were to structure my answer, LCP predicts, then we heat the solution, we are favoring the endothermic reaction. And then I'm mentioning the forward reaction was favored as it increased in blue intensity. Put 2 and 2 together. Thus, the forward reaction must be endothermic. That's it. So that's your structure for your answer. Okay, good. RXN is just reaction, FR is forward, endo is endothermic. Good. So everyone, when I give you those 10 seconds to plan your answer, this is the stuff I want you to write. Don't worry about full sentences. Get the key skeleton out and then articulate it well to me. If you can do those 2 things, you can definitely write a fleshed out answer. Okay? So do a very quick plan in your books when I ask you a question like this. Okay? Good. Ansh, how much time do you normally have? If it's a 2-mark question, how long do you want to spend on it in an exam?
A minute, maybe.
Yeah, so the rule of thumb is if you spend 1.8 minutes per mark, you will finish the exam at 3 hours. You'll have not a single minute or second to double check. So take the 1.8 out of the window. You want to spend ideally about a minute max per mark, and the other 0.8 minutes dedicate that to coming back and double checking your answers. Does that make sense? Good, good. Hi, Gerald. So we were just talking about what we went through last lesson, and we're just explaining LCP questions. Okay, so nothing crazy.
Yeah, sorry, I was late.
No, that's
I didn't know it was late.
yeah, that's all right. I think admin was meant to inform me. I'm not sure what happened, and it was on Teams, but all fine. I've recorded it for you, Gerald. So just go back and watch the first 30 minutes of this lesson to catch up on what we did after class. Good. So now's a really challenging question. And I say it's challenging only because you need to apply your knowledge. I want you to answer 2. If you can apply to the T the things I taught you, 2 will not be an issue. So I'm not going to say anything. I'm going to give you 1 minute to do this question because it requires a bit of thinking. And I want you to think of what traps a normal band 5 or band 4 student would fall into for this question. All right, do we have any ambitious takers for this question? Who haven't I asked? Rabab, you've gone through quite a bit of Mod 5 you mentioned, so I want to see how school has equipped you for this. Take it away.
Okay, so with the 3 questions, first of all, there's I think a decrease in concentration
Of
H2O.
Okay. I'm just keeping everything you're saying. Sorry, Rabab, there's a bit of background now. Okay.
Could you hear me now?
Yeah, it's much better now. All right, so we said that there is a decrease in concentration of H2O. That's what you've mentioned. Keep going.
And so the opposite would be to increase the concentration?
Okay, so which direction are we going?
To the right.
Okay. So your final answer is removing water will cause the solution to become increasingly blue in color. And we're favoring the forward reaction. Okay. Now, who agrees? Raise your hand. Oh, okay. So we have a bit of contention. I think I'll give you a little rule of thumb. I wouldn't have given you a whole minute if it was this simple, right? And that's why I wanted you to think about where students could fall regarding a trap here. Now, I think Pranav might know the answer to this. Pranav, why is this approach not the best approach? Or in fact, I'll get you all to think about this. I think Mithilesh, you've just joined. Hi, Mithilesh. So I've just recorded the first 40 minutes or so. So you can always go back and watch the recording after class, okay? So you haven't missed out on anything. We're just recapping. So Mithilesh, we're looking at this equilibrium here. Question 1, this equilibrium, and the effect of removing water on the equilibrium. And we collectively mentioned that decreasing the concentration of water causes us to increase the concentration of water due to LCP, and thus we'll shift to the right-hand side. What do you think about that answer?
Yeah, it seems about right.
Seems about right. Okay, so Pranav, do you want to clarify to us what the trap was here?
Is it because when you're when you're removing water, you're affecting the volume as well, and
You're very close. Okay, all right. Reset?
Yeah, I think that when you decrease the amount of water, I mean, water is a liquid. It's not aqueous. It's not a gas either. So there is no change in concentration. Therefore, there is no change in any there's no actual disturbance, and therefore there is no therefore neither direction will be favored. The system will stay in equilibrium. There's no effect.
First, I'd like to say very, very good pickup, right? Liquids and solids have a constant density, everyone. You need to think about this. If I gave you water, right, and if I increased the number of moles of water, I would increase the volume of that water as well, right? The concentration of water stays constant. And so we ascribe it a fixed concentration of 1. All solids and liquids have a fixed concentration, which we assume is equal to 1. That's what you need to know for the HSC syllabus. So you can't change the concentration of solids and liquids. Adding them will not disturb equilibrium in any way. That is the first way your exams will trip you up. The second way is reset. You were completely right, but you should have accounted for Pranav's point, which is although water is a liquid and reducing water or removing water is not going to affect water itself because it's got a fixed concentration. What it will do is, if you remember from module 2, C equals N on V. If we reduce water, which is our solvent, that is our volume, what does that do to the concentration of all aqueous species? Come on, guys, inverse relationship. When V decreases, what happens to C?
It increases.
The increases. So we have disturbed the equilibrium. The disturbance is an increase in the concentration of all aqueous species. Does that make sense? This is kind of like a pressure question. Do you all realize that? An increase in pressure is an increase in the concentration of all gases, right? In the same way, when we removed water, it didn't affect water, but it did affect the concentration of all our aqueous species. And so I'd say the reason that we weren't correct in our first approach was because our stimulus was not correctly identified. Do you see how hard sometimes identifying the stimulus can be? This is why I tell you, you need to be so specific for the stimulus. If you're not, you will make silly mistakes. So the stimulus here is in fact removing water is going to increase the concentration of all aqueous species. So what is the opposite of that? Treat it like a gas moles question. So what did we say about gas moles? In our first question, Anj, what did I say you need to have in a gas moles LCP explanation?
The molar quantity.
Good. So the number of moles of reactant, which is on the left-hand side, which is 5, and then number of moles on the right-hand side. What is the number of moles on the right-hand side, everyone? Is it 7 or 1? Gerald, what would you say?
I was going to say 7, but I'm not too sure now.
So my tip to you is liquids and solids, don't care about them. Forget about them. Okay, with equilibrium, you completely ignore liquids and solids. That's my little tip to all of you. Gases and aqueous, very important. They do affect equilibrium. But solids and liquids, forget about it. So it's 1 on the right-hand side, right? Because think about this. We've increased the concentration of all aqueous species. What's the exact opposite of that? Decreasing the concentration of all aqueous species. So we should only count the aqueous moles. Do you all agree? So not the liquid, which is water. Now, which direction would we go? If we want to decrease the concentration of all aqueous species, which direction do we go?
Forward.
Yeah, so the ending is always the easiest part. We go to the right-hand side because we want to favor the production of 1 mole of aqueous product versus 5 moles of aqueous reactant. Now, this question would actually be around 3 marks, because do you all agree you had to first, you'd probably get 1 mark for identifying that water is fixed concentration because it's a liquid. So that would be 1 free mark if you pick that up. Water is liquid, it's got a fixed density concentration. Density or concentration and does not affect equilibrium. Change equilibrium. Now, my question to all of you is, how are you going to write this on paper? You might know your answer well, but you might still lose a mark because you can't articulate your answer. So now I'm going to give you all about 30 seconds. You're all muted, so verbalize it, practice how you would verbalize your answer. And I'll pick one of you randomly in 30 seconds to tell me. This is the exciting part of chemistry. You will rapidly improve because you're learning a lot of concepts that you can pick up, integrate, and you'll see an exponential improvement in your chemistry knowledge. And this is a hard question. So for those of you who didn't get this correct the first go, completely fine. I can guarantee you probably more than half the state who are sitting the exam in 20 days would not get this correct. So good job to those of you who even made a step forward regarding logical thinking. That was very good. Ansh, when you're ready, you can give this question a go. And I want everyone else to look at his answer and think about anything he missed. So a really good student or a state ranked student is a really good marker. That's very important to improve your skills. Because what you want to do is when I finished my chem paper, I had literally 40 minutes to an hour to double check my HSC chem paper. And I went through every single question, marked myself, and I picked up at least 10 marks in the second round. So it's very important you all learn how to mark yourself if you are given a question. So Ansh, when you're ready, take it away.
As liquids do not affect equilibrium, the removing of water only increases the concentration of all aqueous species.
So one second, just slow down with the explanation, just so everyone has a bit of time to digest it and also break it down. So start again.
As liquids do not affect equilibrium, the removing of water only increases the concentration of all aqueous species. LCP predicts that the concentration must partially decrease for equilibrium to be established. This favors the reverse reaction as there are more moles. Oh, there are less moles to balance.
Okay. You all heard that answer. What could be improved? Let me ask Gerald, anything else you'd change with that answer? And you have to be critical, right? I want you to be as critical as you can.
I was confused in the answer because Ansh first states that he doesn't like liquids don't affect equilibrium, but then he goes on again about how to re-achieve equilibrium, he then has to decrease concentration of aqueous species. So would that be like not a really valid explanation?
I would say he is right in the sense that the addition of water, I think he could elaborate that the addition of water due to its fixed density does not directly affect equilibrium. However, equilibrium is indirectly affected through an increase in concentration of all aqueous species. So there you've clarified that there's no direct effect through water, but it's through changing the concentration of everything else. I think that's fine. I'd be fine. I think Ansh, the first party answer was good. Mithilesh, what could be mentioned?
I didn't really catch the second half of the thing because my dad came to ask me whether I've got tuition on.
Oh, right. No worries. No worries.
Yeah, but it sounded about right. Yeah.
Yeah, I would say for the second part of your answer, I didn't hear a counteract, right? And I want to hear counteract in your answer. Okay. So if I had to verbalize this, I'm going to give you all a few seconds. I'll pick one more person before doing so. Athava, I want you to give it a go. What would your answer sound like?
The removal of water won't directly affect the equilibrium, but it will increase the concentration of all other aqueous species. The Shadowless Principle predicts that the forward reaction will be favored as there are more, as it will produce less gas moles and decrease the.
Pause. Sorry, I had to interrupt there. Is it gas moles?
I mean moles of solution.
Yeah. So if you say gas moles, in aqueous,
yeah, yeah.
Okay.
As it produces less moles of aqueous solution, and this will partially counteract and decrease the concentration of all aqueous species.
Yeah, good. I think the last thing you're all missing is you treat this kind of like a pressure question. What did I say for pressure? You need to state the number of gas moles on the left-hand side and on the right-hand side in your answer. Okay, so my answer would sound something like this, along these lines. Okay, I'll give you a bit of time to look at your answer and see how it stacks up. So I'd mention the removal of water will not directly affect equilibrium as the concentration/density is constant. However, the concentration of all aqueous species would increase. The Shadowless principle predicts that the forward reaction will be favored to produce less, now write in brackets, 1 mole of aqueous species on the left-hand side versus 5 moles on the, sorry, I think it's the opposite way. So it's 1 mole on the right-hand side versus 5 moles of aqueous species on the left-hand side, right? And this would be to partially counteract the increase in concentration and return to equilibrium. So do you see I've referred to the number of moles? I've referred to the stimulus, which is the hardest part of this question, and I've referred to partially counteracting the change. Good. So that's how your answer should sound. Does anyone have any questions for question 2? I would like you to circle it or circle it in red. This is probably the hardest like LCP application you can get, which is not too bad. And that tells you a lot. LCP is very straightforward. Okay, so just don't make the silly mistake with state. I hope that's the main thing you learned from today. All right, are we all happy to move on? Okay, so your first set of homework will be to finish the questions on page 55, 56, 57, and so 55 all the way to 60.
So how do we get access to the booklet?
Yeah, so since you all trialed last week, you didn't get access. This week, you'll get access to the booklet. It'll be sent to you via a link on our Teams channel. Okay, so we'll create your access, and then you'll all be sent a link. Basically, what you'll have to do is you have to log into the edX website, and then you need to let admin know your email. And basically, the way it works is your email will give you access to the textbook, so these notes on the website. Okay, so log into the edX website, message admin your email and what class you're from, and they'll register your access. Okay, you should all have admin's phone number, is that right? Yeah, so you can always just reach out to them with any issues regarding access, etc. All right, final question, 1 mark. You don't even need to look at the equilibrium. What is the effect of a catalyst? Let me ask Pranav, and how does that effect get achieved?
So the effect of a catalyst just reduces the rate of reaction, and that doesn't change the equilibrium of the system.
Pranav, I want you to think about this. Does a catalyst reduce the rate of reaction?
Oh no, sorry. Okay. The catalyst increases the rate of reaction, and doesn't affect the equilibrium. So then the catalyst has no effect.
Good. Okay, I like that explanation. And Reesat, do you want to define what a catalyst is? Yeah, 1 line. What is a catalyst?
I would say catalyst is a substance or a species that is used to affect or usually increase the rate of reaction of any of any system.
Okay. Mithilesh, how would you define a catalyst?
A catalyst is a substance that reduces the activation energy of a reaction by providing a different reaction pathway, and it is not consumed up in the reaction process as well.
Very good. Okay, that is perfect explanation. The 2 things I was looking for was a catalyst provides an alternate reaction pathway with lower activation energy. What that means is I'm sure you've all seen your energy time diagrams, right? Where they give you energy of reactants, energy of products. Now, you've also have an activation energy, which is your peak. Now, what a catalyst will do is it'll engage in some other reaction pathway where you'll start to form intermediate products. So instead of going from A to let's say D, you'll make products B and C. And in that process, those reactions have a lower activation energy. And what you'll notice is we need less energy to convert from reactants to your products. So now since you have a lower activation energy, you have a greater number of successful collisions. And if you go back to collision theory, the more successful collisions you have over time, the faster your reaction rate. That's how catalysts work. And very good. He added on that they're not usually used up in a reaction, which is also very correct. Good job. Right. Now, one word I want you all to start using is this term called equilibrium position. Now, a lot of students don't understand this, right? Now, Pranav, when you were saying it does not affect equilibrium, it increases the forward and reaction rate equally, right? And what that does is it doesn't disturb equilibrium because the forward and reverse reaction rates are still equal, they're just a higher number. So they could go from, let's say, 1 molecule converted per second to 5 molecules converted per second for forward and reverse reaction rate, right? But what won't change is what we call our equilibrium position. Does anyone know what this term means, equilibrium position? And I will posit this question mainly to Mithilesh, Rabab, and Pranav as you've gone a little bit further in the module. So what does equilibrium position mean to you?
Okay. It's like the relative amount of products made to the reactants. It's like the relative concentrations of the products and reactants. I guess that's what it means to me.
Yeah, perfect. That's exactly what equilibrium position is, right? Now, remember I mentioned, what is the definition of equilibrium, Ansh?
When the rate of reaction is equal to the reverse rate of reaction.
When forward and reverse reaction rates are equal. Now, what can you tell me about concentrations, Pranav, at equilibrium?
They're always constant.
Good, concentrations are constant, right? So concentrations are unchanging. Does that make sense? Right? They do not have to be equal. That is the biggest mistake you can make if you mention that, right? Concentrations are constant. When we say the equilibrium position lies to the right-hand side, all that means is there is an increase. So think about this, A converting to B. If it lies to the right-hand side, this equilibrium position, all that means is it's in equilibrium. So the forward reaction rate is equal to the reverse reaction rate. But we have a large amount of product relative to reactant. That is what it means when equilibrium position lies to the right. Is everyone with me? Contrastingly, if equilibrium position lies to the left, it's still in equilibrium, so the forward reaction rate and reverse reaction rates are equal, but there is relatively a greater amount of concentration of reactant relative to product. Is everyone with me? Because if you go the reverse way, you produce more molecules of A relative to B, but they're fixed, right? Because since the reaction rates are equal, for every molecule of A you produce, you use up 1 molecule of A. Very good. So hopefully that makes sense to all of us, because now I want you to start using that word, equilibrium position. So catalyst does not affect equilibrium position is what I want to hear. Very good. We happy to move on? Yes. Yes? All right, now we're about to get to some of the more challenging stuff. Here's a very good point. Now, this is a very important dot point that is undertaught, very significantly undertaught at school. And it's this principle that when I say reaction rate, what theory do we use, Gerald? I asked you this last lesson.
Collision theory.
Very good, and you remembered collision theory, right? And when I talk about yield or amount of product produced, what do we talk about? So yield, everyone, if you want to formally define yield, it's your amount of substance produced over its theoretical maximum. Theoretical maximum, and it's often expressed as a percentage. So just to give you a very quick analogy, if I have an equilibrium like this, A to B, everyone, what's the theoretical maximum of B that I can produce? Let's say I've got 10 molecules of A. What's the theoretical maximum molecules of B that I can produce?
10.
10, right? All of A converts to B. That's a theoretical maximum, right? But since it's in equilibrium, it'll be very difficult to disrupt the equilibrium so much that we produce all 10 molecules of B. So if I have 9 molecules of B produced, let's say I've changed the temperature and pressure and reaction conditions, the yield we would say is 90%. The amount of molecules of B we produced is 9, the theoretical maximum was 10, so the yield of this reaction is 90%. Does that make sense? And if I go on to add that this reaction is exothermic, how could I increase yield beyond 90%? How can I disturb this equilibrium?
Decrease temperature.
Yeah, very good. Did you all see that? So what's going to happen, I guess the logic, just to show you all, was Mithilesh was thinking, well, how do I make more B? So I want to shift the reaction to the right-hand side. The 3 questions are stimulus, opposite, and direction, right? Now, when heat is negative, what did I tell you all? Add heat as a product. Makes your life much easier, right? So we're trying to shift to the right-hand side. What is that favoring, everyone? It's favoring the side that's making heat. Does everyone agree? So it's favoring the exothermic. What is the opposite of the exothermic reaction? Endothermic, or reducing heat. So as Mithilesh mentioned, reducing heat will force us to favor the exothermic reaction, shift to the right-hand side, and we increase yield. Do you all see that yield can be explained only through Le Chatelier's principle, right? So this is a very important concept in chemistry. When you talk about rate, you talk about collision theory. When you talk about yield, you must refer to the Shadowless Principle. Now, here's a tough question for you all. First of all, can you raise your hand if you've learnt Le Chatelier's Principle at school? Yeah, so school, your teacher maybe defined it for you, told you. Right. Now, all of you should have had one question with Le Chatelier's Principle. And the question is, did you all have any questions? When I taught it to you, when I said it predicts that when a system in dynamic equilibrium is disrupted, we will partially counteract the change. Did you have any questions when I said that? The question you should have all had was why? Why are we partially counteracting change? Does anyone know why we're partially counteracting change? You need to understand this. Le Chatelier's principle is not an explanation, it's a prediction. Do you all agree? We predict the direction the reaction will go. But why does it happen? Why do these equilibriums seem to be counteracting change? Does anyone know? This is something you need to think really hard about.
Is it because systems want to reach the position of lowest energy?
Yeah, very good. You are right. That is one explanation. So Gerald is completely right. Just in the HSC, they're looking for a bit more detail. So you're completely right. But does anyone know in more detail why?
Is it about like, is it like you have to maintain like equilibrium or homeostasis, I guess? Like it prefers to be in the middle, and then if something happens to it, it'll try to like do the opposite, so it goes back.
Good, good. You're right, Atav. Again, you're explaining it very well. But do you all agree now what we're doing is we're using analogies. We're personifying things. We're saying reactions like to stay in the middle. Reactions don't have consciousness. They don't think. So my question is, why is this happening from a more direct point of view? So you're all completely right. Lowest energy wants to be in its stable state. But why? You might think I'm going to philosophy here, but the answer is Le Chatelier's principle, everyone, is just another way to look at collision theory. Sorry, I wrote collision therapy, maybe because I'm studying a lot of psychiatry for my med school exams, so it's collision theory. I hope you all didn't write that. Good. Collision theory, okay? And Le Chatelier's principle, to recap, is literally a way of predicting collision theory. So I want you to remember this. This is very important. They don't stress it to you in school enough. LCP is an implication or a result of collision theory, full stop. Does anyone care to explain further? Mithilesh, any ideas how? Have you come across this before?
No, not really.
Okay, that's all right. I'll explain it to you all. And this is what they'll ask you in exams. So let's imagine, okay, I'll zoom in here. let's imagine that we've got a reaction, and I'm going to pick the Haber process just because it's so high yield, you know this reaction. So N2 plus 3H2 forms ammonia. And I want you to balance this reaction. That should be balanced. Gas, gas, gas. Pranav, exo or endothermic?
That's endothermic.
Exo.
Exo.
Okay, so we're going to add heat here just to show us it's exo. Now you're going to do two things for me, everyone. You're going to explain the effect of increasing nitrogen concentration using collision theory and then using LCP. The LCP side's easy, right? So I'll give you a quick 20 seconds to predict what's going to happen. So remember, LCP is a prediction system. So tell me and predict what's going to happen according to LCP. Okay, you should have come to an answer by now, right? The focus now for you should be speed and how to write things really well in an exam setting. So with the speed side of things, we'll go to Riasat. What's your prediction? So the 3 questions, answer it for me.
Should I answer it exam-wise or just answer it like?
Just basic 3 questions.
Oh, okay. Okay, so the change is increase in concentration of N2. The opposite is decreasing the concentration, and therefore the direction is the forward.
Good. So Riasat in about 3 seconds has told us that we're going to the right-hand side. Now, you will see he's got an answer very quickly. Now, how would that stack up against collision theory? So in terms of collision theory, I'll guide you all through this. When we increase the concentration of nitrogen, I want you to think about 2 things. What happens to reactant collisions or what happens to product collisions? What do you think will be affected more? When we increase the concentration of nitrogen, will there be more reactant or more product collisions, everyone?
More reactant.
Or reactant.
Going to increase the number of reactant collisions. What is that going to do? Because remember, collision theory, you need to always link it to successful collisions. And a successful collision is when you switch from reactant to product, right? So we're going to increase the number of reactant collisions. So what's going to happen to the number of successful collisions now? Let's say 10% of all reactant collisions are successful. If we increase our reactant collisions, Pranav, what happens to successful collisions?
That also increases as well.
There's an increase in number of total successful collisions. So what can you say now to successful collisions of reactants? You want to be very specific. So Pranav, what is that increasing, the forward or reverse reaction rate?
That's gonna increase the forward reaction rate, gonna make more products.
Good. And so when we favor the forward reaction rate relative to the reverse reaction rate, which direction do we say we're going?
Yeah, right hand side.
Do you all see now how LCP is literally a shortcut to explain collision theory? Do you all see that? So the actual reason why we're shifting to the right-hand side is to do with particle collisions. It's not to do with a system that loves sitting in the middle. It's solely because when you increase a reactant concentration, you're going to increase the number of reactant collisions and successful collisions. And that's going to favor the forward reaction relative to the reverse reaction. Now, if you had to draw this on a graph, what would this look like? So imagine this is your reaction rate time graph. And let's say at time equals 0, we've increased our concentration of nitrogen. Now, initially, does everyone agree a forward and reverse reaction rate are equal because it was at equilibrium? Everyone with me? But then what's going to happen is when we increase our concentration of nitrogen, we slightly increase our forward reaction. So our forward reaction will temporarily increase. Does that make sense? Our reverse reaction will relatively stay the same. Or will it stay the same? I want you to think about this. So your forward reaction is increased. What's going to happen to the reverse reaction? Very good thought, principle. They might give you an exam question on this.
Wouldn't it decrease?
Why or why not?
Because
I'll give you the reaction to help you out. We said our forward reaction will increase. What will happen to the reverse reaction?
Would it slightly increase as well, but just not as much as the forward?
Okay, why do you say that?
Because when there's more like ammonia particles, or like on the
So
like-
you've actually come to a very important point. Does everyone agree when we increase our forward reaction, what are we doing? We're converting this to this. So what is that doing to our concentration of product? Increasing its concentration. What's it going to do to the number of collisions of our product particles? Increase. What is that going to do to the reverse reaction rate? Does everyone agree? So what will happen is you will see a bit of a lag, right? So while your product particles are forming, there won't be much of a change. And then what you'll see is slowly, you'll see the reverse reaction rate also increase as such. Okay? And then eventually what should happen is they should equalize, right? So eventually your reverse reaction rate and your forward reaction rate will meet and they become stable again. Good, something like this. Okay, that's just to show you what will happen. So they'll eventually meet one another as well. And the increase should also be not in that direction, it should be like this. Both of them should increase at a decreasing rate. That's what it would look like. Okay, so that's the nitty gritties. Don't worry about the reaction rate time graph. Just focus on this. This is what your exams will ask you. Okay, so does everyone now understand how LCP is an implication of collision theory? This is very high yield. Exams love to ask this because a lot of students don't understand it. Okay, good. Are we ready to try another question? Okay, I'm going to give you the other end of the spectrum, which is explain using LCP and collision theory the effect of decreasing ammonia concentration. It's a little bit harder, but you can do this. What would be the effect of decreasing ammonia concentration? So LCP can quickly answer that, and then you're going to have to think a little bit with collision theory. So Rabab, maybe start us off with the LCP side of things. What are the three main questions, and what's your conclusion on which direction we favor?
So it's originally increasing concentration of ammonia.
Oh, what direction is the arrow pointing?
Decreasing, sorry.
What's the opposite?
So the opposite would be increasing.
So which direction are we going?
Oh, we're going to the left.
Think about this. How do we increase ammonia? We point an arrow that makes more ammonia. We favor the reaction that makes more ammonia. Do you agree?
Right, yeah.
So which direction are we going?
Forward.
Good. Right-hand side. So Rabab has very quickly told us our answer according to LCP. Now, here's a long-winded explanation. What happens according to collision theory? So hopefully you're all realizing collision theory can explain yield as well. It just takes much longer. So we use LCP. It's a prediction system as to what will happen based on collisions. Think this one out, please, because it's a bit of a conceptual one. I want to see who can apply the knowledge that they've learnt from year 11 and from the past two lessons. And I promise you, after this question, you all get your break. Well deserved.
I think I got it.
Okay, very good. So, Asapa, very bold. Good job. Take it away.
So when there's a decrease of concentration of the ammonia particles, that means there's less product particles in the system.
Let me just scroll back down over here. Good. So, yep. So you were mentioning, sorry, start again.
So since there's a decrease in the concentration of ammonia particles, that means there are less product particles in the system.
Yeah.
And that means that the more reactant particles will be colliding because there's less products. And that means the number of successful collisions for the reactants will increase. And then like that.
So it's all relative. I'll pause you there. You're completely right, but I'm just going to tweak your answer a little bit, which is that I would mention, since there's less product particles, there's less total and successful collisions of your products. That's how I'd start off. And I'd say, therefore, relatively, there are increased reactant collisions, increased successful reactant collisions. So then which direction do we go if there's increased successful reactant collisions, everyone?
Forward or right.
And guess what? What did LCP predict? Predicted would go to the right. And guess what? We do go to the right, according to collision theory. Very good. So it will be your job, if they ever ask you a question to explain LCP according to collision theory, this is how you do it. Okay, so very good job, Athar. That's just a small tweak I'd make, is I'd explain everything at products, and then I'd end it off by saying, thus, relatively, there's increased reactant collisions. I'd keep that to the very end. Okay, very good though. I'd still give you full marks. I'm just perfecting your answer. Does that make sense to everyone? Did you all come to the same conclusion? Good. Okay, you ready to now do a more challenging question? We can do it after the break. How about that? Because we've hit the hour mark. What I'll do is you will take a 5-minute break, stretch, stand up, get some water, and we will resume at, what's the time now? 2:53. We'll resume at about 2:58. How does that sound? Good. Good job. All right, everyone. See you all in 5 minutes. Get some water, stretch, move around. Okay. When we're back, you can all turn your cameras back on. Let's jump back into it. All right. So what I'm going to do now is I'll give you a HSC question to actually try out, and we'll see how we go for this. So HSC Chemistry 2020. So have a look at the paper. I think I've shown some of you this paper previously. And here's one question you can try out. So again, apply the principles that you learned with me so far. And this will help you with this question. This is question 16. So a little tip, going from question 16 to 20 in your HC exams, those tend to be the most challenging MCQs, and those will take much longer than a minute. So I think anticipate this question will be a bit longer than a minute for you. I'll give you 30 seconds to start, and then I'm going to start asking people their approach.
What does the MPa stand for?
MPa is megapascals. So PA is the unit of pressure, which is pascals. And kilopascals would be 1,000 pascals, and megapascals would be 1,000 kilopascals. So it's technically 1,000,000 pascals. Not important, just know it's a measure of pressure. That's all you need to know. Good question. Does anyone have any other questions so far? Okay, I guess I'll start picking on people. First of all, looking at this question, what makes it challenging, Pranav? Looking at the graph, what about the graph is challenging to interpret?
It's not giving me much. Like, it's just like just curved lines.
Yeah, sure. But specifically, more specifically, the reason this graph is challenging is because there are 3 axes. Do you all see that? The third is technically not an axis, but it's its own unit that you need to be referencing and controlling for. So there are 3 changing metrics, and you're used to only seeing 2 on a graph. That's the first reason you find this question hard. Okay? The next question is that there are many things changing, and there's many numbers in the reactions as well, which you don't know their significance, but you will very shortly. Now, what you need to be doing in a chem question is underlining the key words. So you've been told that it's an equilibrium, and what did I tell you all? You can assume most of the time when they say equilibrium, they're talking about your dynamic equilibrium, and you can confirm that because every reaction pathway is reversible. Does that make sense? So you can straight away say this is going to obey Le Chatelier's principle. Now we're looking at temperature and pressure on equilibrium yield of Z. What was the definition of yield? Who wants to define that for me again, just so you understand? So let me ask Riyasat, how do you define yield?
Yield is the percentage of the amount of products of form from divided by the theoretical maximum.
Good, right? So it's the amount of substance divided by theoretical max, usually expressed as a percentage. And the way we increase yield, usually when they say substance, they're talking about the product. 90% of the time, when they talk about yield, they're talking about the product. Do you all agree Z is the product for all of these reactions? Everyone with me? So how do we increase yield of Z? We need to shift the equilibrium to the right. It's that simple. Make sense so far? Good. Now let me help you interpret this graph. So what you need to do is, you'll agree, there is one x-axis, which is your independent variable, which you can start moving along. And there are two other variables that are also changing, right? So what you need to do is you need to look at one variable at a time, okay? Now, we said yield is a measure of how much we're shifting to the right-hand side. Does everyone agree? So I'm just going to write yield equals shifting to the right-hand side. Now, Gerald, I want you to pick one of these because you can't look at both at the same time. Temperature or pressure? Pick one for me.
Temperature.
Good. So if you're looking at temperature, Gerald, you must fix pressure, because if you're looking at changing temperature and pressure, you're going to muddle your brain up. So we need to fix the pressure and look at how temperature changes the yield. Does that make sense to everyone? We want to look at one factor at a time. So Gerald, I want you to quite literally pick any of these pressure curves. Pick only one.
10 megapascals.
Good. So what you're going to do in your head is you're going to forget all the other pressure curves. So I'm going to just scribble them out, forget they exist, solely look at this fixed pressure. And what you're going to be doing is you're going to increase temperature and look at how that affects the yield. Is everyone with me? Okay. Now, as I increase temperature, what's happening to yield? Just looking at that curve there. As my temperature goes up, what's happening to yield, everyone?
Increases.
Good, right? So what were the three basic questions we always ask ourselves with LCP? Mithilesh? What are the three basic questions for LCP?
Sir, he dropped out temporarily. He left temporarily, so we asked him again.
Okay, good. Ansh, what are the three basic questions you ask yourself for LCP?
The change, the opposite of the direction.
Good, right? So what do we know so far, Ansh? We know that when we increase temperature, we are increasing yield. So which direction are we going to then? What's the direction? Good, so we can say direction is right-hand side. Okay, and what was the stimulus?
Increase in temperature.
Yeah, very good, because that's what we did, right? We increased temperature. We looked as we shift to the right on the axis. What's the opposite of increasing temperature, Ansh?
Decrease.
So which reaction are we favoring, exo or endo?
Endothermic.
Yeah, if you want to decrease temperature, you want to favor the endothermic reaction. Put two and two together. The direction is the direction you go to favor that opposite. So the forward reaction must be endothermic. See, you don't even have to think. LCP is that easy. You just have to ask yourself those three questions, fill out the three questions, and you're done. So straight away, what can we cancel out now, Athava?
I can cancel out B and D.
B, cancel out. D, cancel out. Are you sure? Yes, you are correct, because those are exothermic reactions. Good job. Right, so we're now stuck between A and B. Now, everyone, what's the difference between A and B? Do you all agree it's the numbers? Right? Everything else is the same order, X, Y, and Z. It's the numbers. Now, when were numbers super important to us? When did I tell you to block things out and count the numbers on each side?
Pressure.
Pressure. So you're going to get your final answer by looking at pressure. So we're going to apply the same principle here. So now I'll pick on, let's get Rabab, you're going to answer this one for us. So Rabab, I want to look at pressure. So what should I do to temperature? I want to fix it. Do you agree?
Yeah.
So pretty much what you do is you fix a random temperature. Just draw any random vertical line and fix that temperature. We're not going to move from that point in our x-axis. Does that make sense to everyone? We're not changing temperature. Look at how the pressure affects yield. As I go from 10 to 30 to 50 megapascals, what's happening to the yield?
It's increasing.
Think about this.
It's going down, sorry, decreasing.
Decreasing, right? So as you go from 10 to 30 to 50 megapascals, the yield is dropping from here to here to here because the yield is a y-axis. So again, the three basic questions, right? Reset, you're going to answer these three basic questions now. So what was the stimulus that we did?
The stimulus is increasing the pressure.
Yeah, you could do it either way. Yeah, so increase, decrease pressure. So you're right, it's an increase in pressure as we went from 10 to 30 to 50. So stimulus is an increase in pressure. So what's the opposite of that?
The opposite is decreasing pressure.
Good. Now, what happened to yield?
The yield decreases, so the left-hand side is favored.
Very good. Good job. So I think you're all getting the point now that yield is solely how much you've shifted to the right. Good job. So we are going to favor the side that has decreased pressure, aka are we trying to favor less or more gas moles?
Less.
Less.
We're trying to produce less gas moles and put two and two together. Remember, the direction is the direction we go to favor the opposite. So that tells me the left-hand side must have less gas moles. In which option does the left-hand side have less gas moles?
C.
Right. C. How easy was that, right? I honestly didn't have to think that hard. It was just following the same steps. And the hard part for students was number one, interpreting the graph. Number two, the second you see fancy graphs like this, students start kicking these basic principles out the window and they start freeballing it. The second you do that, you're going to get stuck. Okay? So stick to those basic three questions. You will always get it right for LCP. Do we have any questions so far? Good. Good job. All right, let's move on. Let's do easy. There's a really good question here about temperature, which is why I wanted to bring this up for us. Let's see if I can find it. There you go. So I think I told you how high yield it is that they're going to ask you about equilibrium with reference to with collision theory, right? So this is literally testing the dot point, which we're learning now. A lot of students found this question hard. Now, I just want to emphasize this. I haven't taught you all KEQ yet, and you don't need to know KEQ to answer this question, so I'll give you the information you need. KEQ is a measure or a quantitative number that we use. It's a number that we've created to measure the equilibrium position. What is the definition of equilibrium position again? I'll ask Atharva.
It's like if there are more products or reactants, like if it's to the left, there are more reactants than products, but it's still in equilibrium.
Very good. So the KEQ, this is a very crude simplification of the formula. It's a bit more complex than this. We raise things to the power of their stoichiometric ratio, but the simple fundamental to answer this question, all you need to know is the KEQ is calculated by getting the concentration of products and dividing it by the concentration of reactants. Beyond that, you don't need to know anything about K. We'll come back to K because that's the second inquiry question of Mod 5. For now, give this question a go. So 4 marks means you'll get 1 minute to plan your answer. And remember this, if it's 4 marks, you should stop and plan your answer. In reading time, I would have already had a little plan in my head. I'm going to give you a 1 minute to think this through. This is a challenging one. Okay, by now you should have thought things out, had a bit of a plan. So let me start you with this. When you're stuck in chemistry, in general, what are the fundamental steps you need to apply first? Before even thinking about LCP, equilibrium, all of that, Pranav, what's the first thing you always do with any chemistry question?
Equation.
Good, right? We don't have an equation. How about we write one for ourselves? So what is the equation?
N2O2 plus O2 gives
Remember,
NO.
it's They're different substances. Good. And they give?
NO, and then balance it.
Good. Good job, right? So it should say these are all gases. Does it say that here? No, doesn't matter. But you should know vaguely that diatomic particles are typically gases. And NO is also a gas. But okay, let's continue. Now, what are we being asked? How an increase in temperature would affect KEQ or equilibrium. So now you can start thinking, well, I've done my equation, I've balanced it. There's no data, there's no numbers in this question. Does everyone agree? So there's no data I need to write out. So then the next step is, well, what's a specific question type? It's an equilibrium question. So what are the 3 questions we always ask ourselves? See how much it repeats? It's always the same question, just different approaches. So Gerald, take us through this. An increase in temperature, what do we know from a stimulus opposite direction standpoint?
Well, there's an increase in temperature, so the opposite would be a decrease in temperature.
So what reaction will be favored, exo or endo? Remember, that's the most.
It would be the exothermic. No, sorry, endothermic.
Right. Exo will release heat into the environment, increasing its temperature, so favoring the endothermic reaction. Do we know the direction? No.
Forward.
Oh, we don't know. We don't know yet. Do you agree? Yeah. You don't know whether this reaction is endo or exothermic. You don't know whether this forward reaction sign is positive or negative until you look at the graph.
Yeah.
So now look at the graph and tell me, this is your reactants, and this is your products. So now, can you tell me what is the enthalpy sign for the forward reaction?
It would be positive.
Yeah, very good. So it's absorbed energy, so it's endothermic, or we can write heat on the left-hand side now. Does that make sense? Very good. So decrease in temperature, which direction are we going? To the left or to the right? And I'll ask Tanisha this. If we're having an endothermic reactions, are we going to the left or the right?
To the right.
Think about
Sorry,
it.
left.
Yeah, very good. Because if you're having the endothermic, wait, are we going to the left or the right? What's our final answer? I think I confused you. Sorry, Tanisha. If we're having the endothermic reaction, the forward reaction is endothermic. I should have written triangle H is positive. So if we're having the forward reaction, you're completely right. We're trying to decrease temperature, so we'll use up temperature as a reactant, and we'll favor the forward reaction. So you're completely right. Good. So we understand it from an LCP point of view. Can anyone explain it from a collision theory point of view?
Yeah, I'll give it a shot. So as we can see in the graph, the activation energy for the forward reaction is much higher relatively to the reverse reaction.
Good.
And so when we increase temperature, we're increasing the average kinetic energy of the particles. And when we do this, for the forward reaction, there will be a proportionally larger increase in the amount of successful collisions compared to the reverse reaction, as the reaction as the activation energy is higher.
Good.
What was the question again?
So it pretty much explain how it's going to affect KEQ.
Oh, okay. Yeah. And then we can see that because of that, the forward reaction will be favored, as there'll be a greater increase in its reaction rate. And so we can see that there'll be more products formed compared to reactants. And as the concentration of products goes higher and the concentration of reactants goes down, the value of KEQ will increase.
Very good.
Yeah.
I would say, honestly, that's a very close to perfect answer. Very good. Good. So I think let me just run through what he's mentioned, and I'll explain to you how to think about this, right? Because he's given us a very good exam written answer, but I'll show you how I think about this from a very basic perspective, right? I want you to imagine that you are here and your mate is on the other side. You're both trying to climb up to maybe your picnic at the top of this mountain, right? Now, who's going to have a harder time climbing up to the top of the mountain? You. Do you all agree? Because you're much lower. What happens is when you increase temperature, has anyone played Mario Kart? Anyone go on, you know, the mushrooms that you hit the mushroom and you speed up in energy, it's a boost of energy. That's how temperature affects a reaction system. So when you increase temperature, the kinetic energy of all the particles increases, aka every single particle, including nitrogen, oxygen, and nitrogen monoxide, all increase in their energy. So they all get a bit of a booster. So imagine you're pretty much playing Mario Kart, and now you get a huge booster. Now I want you to ask yourself, who will this booster help more? This guy's pretty much at the top. He doesn't need a booster. Whereas you at the bottom, do you all agree, you need much more kinetic energy, and that's going to proportionally help you much, much more. So what happens is when we increase kinetic energy, that will preferentially, in this case, increase the rate of forward reaction more than the reverse reaction. And from a chemical point of view, I'll show you how to think about this. In chemistry, you can think of it as, since the reverse reaction rate has such a low activation energy, I want you to imagine at a temperature, fix a temperature, 99%, we're going to pick extremes here, 99% of nitrogen monoxide already will engage in successful collisions. Is everyone with me? Whereas the forward reaction rate, since the activation energy is so high, let's imagine only 1% of particles in the forward reaction will engage in successful collisions. Is everyone with me? Now, when I increase kinetic energy, the max I can improve this reaction rate by is by 1%. But what's the maximum I can increase this reaction rate by? Technically, theoretically, 99%. So when I increase kinetic energy, do you see how it's disproportionately increasing the successful collisions on the reactant side compared to the product side? Good. So think of it how you'd like, but make sure you have a conceptual way to understand this question, and then make sure, like Mithilesh, you have an exam structure to your answer. So what he's written is quite literally would be the sample answer. So I've just copied down the key points, which is the forward reaction increases more than the reverse reaction. Kinetic energy of all particles increases. And I guess the key step that students often miss is that this will increase the forward reaction rate proportionately greater than the reverse reaction rate. And thus we get increase in forward relative to reverse, or we shift to the right-hand side. Very good. So now hopefully you understand. Do you see that we've just used collision theory to explain the Shadowless Principle? Does everyone see that? So I hope now you will never ever forget that the Shadowless Principle is a prediction system that is an implication of collision theory. Make sense to everyone? Good, good job. Happy for me to move on? All right, very good. Let's go back to our content. So good, we finished all of that. You can read all of this in your own time, and you can answer these questions. So page 60 up to 65 is all about collision theory explanations. So we'll come back to this. Now, I'm going to start introducing you to graphs. I would say this is the highest yield part of Module 5. There are two very important high yield aspects of Mod 5. Number one is your concentration time graphs. Number two is your K and Ksp calculation questions. The vast majority of Mod 5 will relate to these. Okay, so everything you've learned up till now is the very, I guess, the easy, the foundational things. We're now going to move on to the very high yield stuff. Okay, so what did we say about reaction rate at equilibrium, everyone? Did we not say that they equal? Do you all see here that the forward and reverse reaction rates eventually equalize, and that gray region of the graph is the equilibrium region? Look at the y and look at the x-axis. Now, question to all of you, Ansh, is this a static or dynamic equilibrium reaction rate time graph?
Dynamic.
What would a static equilibrium reaction rate time graph look like? So back to
Would it
you,
just
Ansh.
be one line?
Pardon?
Would it just have one line? Since the reaction rate of the reverse reaction is always 0.
Yeah, so you would still draw the reverse reaction rate, but you'll emphasize it's at 0, and the forward reaction rate will continue until it drops to 0, right? And let's say it reached equilibrium at the same time point, it would look something like that. Everyone with me? Good. So that's all you need to know. This graph is very low yield because do you see how there's not much you can think about from this graph? It's just they equalize, you know it's at equilibrium. The higher yield graph is this one. What do you notice is different about this graph? So Riyasat, what's different with this graph?
The difference is that the concentration, yeah, it is the concentration, not the rate, which is
Very
why, it's on the graphs aren't equal. They become constant and equilibrium.
Very good, right? So he's applying the principles that he's learned, right? So this is a concentration time graph. And what you will notice is that the system, when it reaches equilibrium, the concentrations become constant. Are they equal though? Have a look at this. They're not equal by any means at all, okay? And the only reason hydrogen and iodine are even equal is because they had the same initial starting concentration. And if you draw the reaction out, you would get Hi decomposes to H2, and it would be the opposite for this because we started with a high concentration of Hi. So it's a H2 plus I2 combined to give you Hi. And you would notice they have an equal stoichiometric ratio. Does everyone see that? So they'll be subject to the same change in concentration. That's the only reason they're equal here. So that's by chance. It's a very rare occasion that happens. So all you need to know is that concentrations are constant at equilibrium. Okay? And I'm going to start you all by throwing you in the deep end here. I'll give you a slightly different one. Let me give you this. You'll get something like this in your exam, and it looks like it's a roller coaster, right? 3 roller coasters moving along each other. We'll focus on T1. We'll start at T1. What reaction is this, first of all? Keeps coming up. Sava?
The Haber process.
Yeah, very good. So he's picked up the Haber process, so you can quickly write the equation, because remember, you need an equation to understand these questions. So we'll put a 2 here and a 3 here. Now, can anyone tell me what the disturbance at time 1 is? Because you'll agree the concentrations are constant, which means it was at equilibrium up until time 1, and something messed it up. Gerald, what are the 3 ways I can disturb an equilibrium?
Change in concentration of substance, change in temperature, and
Pressure volume. You need to have
pressure volume. Yeah, that's
okay.
awesome.
So one of those 3 has resulted in that disturbance at T1. Now, can anyone tell me what that disturbance at T1 is and why? I might get Pranav to explain this one.
So there is a increase in the concentration of nitrogen.
Okay, so does everyone see this big spike in only nitrogen? Forget about everything else. Everything else, you'll agree, is changing gradually and slowly. Focus on the salient change. The salient change is that at that point in time, so freeze time at T1, something rapidly changed, and it was nitrogen. So what does that tell you the disturbance is, Pranav?
The concentration of nitrogen adding, the increase here.
Good. So the opposite is a decrease, and as you know, which direction are we going?
We're going towards the right side.
Good. And Tanisha, if we're going towards the right-hand side, what would you expect to happen to the concentration of ammonia due to the Shadowless Principle?
It would also increase.
Yeah, so do you see this gradual increase in ammonia, right? And what's going to happen to the concentration of hydrogen? What will happen to it?
That would decrease.
Yeah, do you all see that gradual decrease? And then do you all see it stabilizes around there? And we can say at that point, equilibrium has been reestablished. Very good. Now I'm going to introduce you to 2 phases, and you need to think of equilibrium concentration time graphs as having 2 phases always. There is always going to be an initial phase. Does everyone see? There's an initial phase where nothing changed except for one huge disturbance. And sometimes all 3 of them can change, sometimes none of them can change, but it gives us a clue into what the stimulus was. And does everyone see after that initial stimulus phase, so again, label this your stimulus phase, we have a phase where everything is gradually changing. Does everyone see that? Curves. Everything's changing in a very curved manner. This is what we call, I'll do this in a different color. This region is what we call the counteraction phase. Counteraction phase. Now, one of these phases is obeying Le Chatelier's principle. Can anyone tell me which phase is operating in accordance to Le Chatelier's principle? Fatava?
The counteraction phase.
Good. So obeys or operates, or you can say it can be explained by Le Chatelier's principle. You can always explain the counteraction phase by LCP. The stimulus phase has nothing to do with LCP. It has everything to do with the disturbance. So all I want you to remember is a stimulus phase is used to identify the disturbance. That's it. Good. Any questions so far? Okay, good. So let's have a look at the rest of these graphs. Now, I want to just preface this. Reading these graphs is easy. Drawing these graphs is harder. Okay, and I'll show you what I mean next lesson when I show you how to draw the graphs. But good. So hopefully you'll understand the basis of approaching the concentration time graph. Next lesson, we'll finish off. Maybe I'll keep all of this here. Next lesson, everyone, we'll finish off by having a look at this region of our graph. Okay, and I'll take you through how to draw your concentration time graphs. And if you're all quick, we would already start K calculation questions. And that would be my goal, which would mean you're pretty much 30% through the module already. What, 3 lessons? Which is very good. I'd say maybe 40%. Good. Do we have any questions so far? All right, good job. Does anyone have any general questions? How to study chemistry, what you should be doing now, time points, anything at all?
How do we access the booklet again?
Yeah, the way it's going to work is you log into the edX website with your Gmail, and then you message admin your Gmail. Okay, and then they'll give you access to the. I think admin would already have access to all of your emails because you would have provided that on enrollment. So in fact, I think you'll all get automatic access. So I think I'll message you on the Teams channel how that all works. Okay, so just make sure you're checking that regularly, and on one of these weekdays, you'll get a message from me or admin saying you all have access. Here's a link to the page, and just sign in via your Gmail account. Okay. Good. Now, the other thing I want to mention is specifically for the Sydney Boys students. I will be merging this class just for the next couple of weeks, only because I'm sitting mock exams in my final exam all the way until about the 9th of November. Okay. So after that time point, we will have a Sunday class and Saturday class as well, as then I'll have time for Sundays. Is that okay with all of us? Good, good. So I'll see you all then next week. Saturday at 1:30. Good. Enjoy your week. Have fun.
Prithvi, I have a question for you. So I'm doing a SAC assignment, right? And for that, I'm going to need to interview people. So about what age are you?
I'm about 22.
Okay, because I'm investigating the, what do you call it? How independence is, or how sociocultural influences the independence of like South Asian youth.
Okay, sure. I'm happy to fill out your form if you have a form.
Yeah, it's not yet. I'm gonna need to do like a focus group and like get more people, and yeah, it's like a whole hassle. So it's gonna be fun.
Yeah, that sounds pretty exciting.
But cool. Yeah, okay. Thank you.
Cool. All right, everyone. Enjoy your week. See you all next week.
Okay, see you. Thank you.
All right.
Bye, sir.
All the best.
Accept.